We discussed power series in the previous lecture. Today, we will have radius of convergence and interval of convergence of a power series. Here are the objectives for this lecture. At the end of the lecture, you should be able to determine the radius of convergence of a power series and determine the interval of convergence of a power series. Let us generalize what we have discussed last time regarding power series and geometric series. A power series in the form summation of u to the m from m equals 0 to infinity, where u is a function of x in the form u equals ax to the n, can be written as a rational expression equivalent to 1 over 1 minus u, or 1 over 1 minus ax to the n, with the limitation that the absolute value of ax to the n must be less than 1, or the absolute value of x must be less than the nth root of 1 over a. Again, if the power series is in geometric series form, we have the following generalization. The power series given by the summation of ax to the n raised to m from m equals 0 to infinity is equivalent to 1 over 1 minus ax to the n if the absolute value of x is less than the nth root of 1 over a. And the radius of convergence of the series is given by rho, which is the nth root of 1 over a. Now, what happens if the power series is not in geometric series form? What is the radius of convergence of the given power series? So given a power series, there will exist a number rho between 0 and infinity so that the power series will converge for the absolute value of x minus x of 0 less than rho, and will diverge for the absolute value of x minus x of 0 greater than rho. This number rho is called the radius of convergence. To determine the radius of convergence of a power series, we are going to use the ratio test. So the radius of convergence of a power series can be determined by the expression L equals the absolute value of x minus x of 0 times the limit of the ratio of a sub n plus 1 and a sub n as n approaches infinity. If L is less than 1, then we say that the series converges. If L is greater than 1, the series diverges. And if it happens that L is equivalent to a function of x, then the series may converge or the series may diverge. The ratio test can be presented in three forms. The first one is if the base of the power series is a binomial x minus x sub 0. The second is if the base of the power series is simply a monomial of the form x. And the third one is L equals the limit of u sub n plus 1 over u sub n as n approaches infinity. Let us have some examples. So determine the radius of convergence and interval of convergence for the following power series. Number 1, the summation of n factorial times x minus 2 raised to n as n approaches infinity. Second, the summation of x raised to k over k plus 1 factorial from k equals 0 to infinity. And third, the summation of 2x minus 6 raised to m as m approaches infinity. Let us solve the first number using the first formula. So given the summation of n factorial, times x minus 2 raised to n from 0 to infinity, let us use L equals the absolute value of x minus x sub 0 times the limit of the ratio a sub n plus 1 over a sub n as n approaches infinity. But what is a sub n? So a sub n is equivalent to the coefficient of the power term, so that is n factorial. So we will end up with L equals the absolute value of x minus 2 times the limit of n plus 1 factorial over n factorial as n approaches infinity, since a sub n is n factorial and a sub n plus 1 is n plus 1 factorial. So how are we going to evaluate the expression n plus 1 factorial over n factorial? Note from lower math that 5 factorial over 4 factorial is equivalent to 5. So by inspection, n plus 1 over n factorial must be equivalent to n plus 1. So therefore, L is equivalent to the absolute value of x minus 2 times the limit of n plus 1 as n approaches infinity. Now, as n approaches infinity, your n plus 1 also approaches infinity. So we will end up with L equals the absolute value of x minus 2 times infinity. But infinity multiplied by any number is equivalent to infinity. So therefore, L must approach infinity. And if L approaches infinity, then we say that the radius of convergence must be 0. So since L is greater than 0, then the series diverges for all numbers except 2. And we say that the radius of convergence is equivalent to 0. Using the second formula with a change of variable from n equals 2 to k, we can solve for the second number. So given the summation of x to the k over k plus 3 factorial from 0 to infinity, we will use the formula L equals the absolute value of x times the limit of the ratio of a sub k plus 1 over a sub k as k approaches infinity. So, L is equivalent to the absolute value of x times the limit as k approaches infinity of 1 over k plus 4 factorial divided by 1 over k plus 3 factorial. So how do we simplify this complex expression? So we reciprocate the denominator, ending up with k plus 3 factorial over k plus 4 factorial. And then we simplify the expression, and we will end up with L equals the absolute value of x times the limit of 1 over k plus 4 as k approaches infinity. Now, if k approaches infinity, then 1 over k plus 4 will approach 0. And we say that L is equivalent to absolute value of x times 0, or simply equivalent to 0. And if L is equivalent to 0, then the radius of convergence must be infinity. And we conclude that since L is less than 0, then the series converges for all x. And the radius of convergence is rho equals infinity. The interval of convergence is equivalent to negative infinity up to positive infinity. Using the third formula with a change of variable from n to m, we can solve for the third number. So, given the summation of 2x minus 6 raised to m from 0 to infinity, let us use the formula L equals the limit of u sub m plus 1 over u sub m as m approaches infinity. So what is u sub m? Your u sub m is equivalent to 2x minus 6 raised to m. So therefore, u sub m plus 1 is 2x minus 6 raised to m plus 1. Using algebra, okay, we can simplify this to absolute value of 2x minus 6. Now, how do we evaluate limit of 2x minus 6 as m approaches infinity? So we recall from calculus that the limit of a constant is equivalent to the constant. Since 2x minus 6 is considered as constant as m approaches infinity, then we say that L must be equivalent to the absolute value of 2x minus 6. Now, since the result is a function, so we have to solve first for the radius of convergence by saying that the absolute value of 2x minus 6 must be less than 1. So using algebra, factoring, absolute value, inequality, and continued inequality, we can determine the radius of convergence and the interval of convergence for the given power series. So if L is equal to the absolute value of 2x minus 6, then we say that the absolute value must be less than 1. By factoring, we will end up with 2 times x minus 3 must be less than 1. Division will give us the absolute value of x minus 3 must be less than 1 half. Okay? And after that, we say that the radius convergence is equivalent to rho, which is 1 half. Now, let us determine the interval of convergence. So we can rewrite an absolute value inequality using continued inequality. That is, the absolute value of x minus 3 less than 1 half is the same as the continued inequality negative 1 half is less than x minus 3 is less than 1 half. We then transpose negative 3 to the left and we transpose to the right. So that is negative 1 half plus 3 is 5 halves, while 1 half plus 3 is 7 halves. So we now conclude that the interval of convergence is the open interval 5 halves to 7 halves. So let us conclude based on the three examples. So convergence of power series. Exactly one of the following must be true. First, the power series converges only for x equals x sub 0. The second, the series converges for all x. And the third, there is a number rho such that the series converges for all x less than rho and diverges for all x greater than rho. It may converge or diverge at the endpoints x equals rho. That's all for the discussion of radius of convergence and interval of convergence of power series. Next time, we're going to discuss differentiation and integration of power series. This is Redentro Disles. Have a good day.